Good day everyone. So for today's topic, we will discuss forces in an inclined plane with friction. So previously, we have discussed forces in an inclined plane but in a frictionless surface. So this time, we will discuss forces in an inclined plane with friction. So looking at the diagram, so for the box on the top of the surface, we can identify that there are two forces acting on it. So that is weight and that is the normal force. Now, if we will incline this surface into a certain angle, just like this, so definitely this will accelerate. So as we discussed before, we can stop this box from accelerating if we will apply an applied force or a tension. But in this case, even though there is no applied force and there is no tension, we can still stop this box from sliding if the surface has enough amount of friction force, which is this. So friction is defined as a force that is always opposes to the sliding. So this box has a tendency to slide downward, and this force is always parallel to the surface. And the symbol of that is F. So what are the other forces acting on this box? So that will be the weight, which is always going down, and the normal force, which is always perpendicular to the surface. So if we will put this in a free body diagram, we will assume that our surface is always the x-axis and normal force is aligned to positive y-axis. So it will be normal force, friction, and the weight. We also learned last topic that the angle theta will be the angle between negative y to the force of the weight. And just like spring force, friction, it also depends on the type of the surface of the object and the type of the surface of the inclined plane or the surface itself. So to account that one, we will have the formula for friction, which is friction is equal to the coefficient of friction times normal force. This coefficient of friction depends on the different surface of the object and the surface. So here, these are the examples of the values of different surface. So for example, I have a steel object on a steel surface, or aluminum object on a steel surface, or aluminum surface on a steel object, copper on steel, rubber on concrete, and so on. So these are the values that we have as our coefficient of friction. If you want to know what is the coefficient of friction of the object and the surface, you can easily get it by dividing the friction force divided by the normal force. And since friction force has a unit of Newton and normal force has a unit of Newton, so therefore the coefficient of friction is unitless. So other than that, as you can observe, there are two sets of coefficient of friction. So we have here the mu s, or the coefficient of static friction, and mu k is the coefficient of kinetic friction. And as you can observe, mu s, or the coefficient of static friction, is always greater to the coefficient of kinetic friction. So the idea here is you have to apply a greater force if you want to move the object from at rest. Now, once you reach the maximum static friction of the object and the surface, and you break loose on that maximum force or the force of the static friction, you can now apply a lesser force because the coefficient of kinetic friction is lesser in this kinetic region. So since in static region, the coefficient of static friction is greater, so you have to apply a greater force. While for the kinetic region, since the coefficient of kinetic friction is lesser, so the friction is lesser, and to make the object moving with constant velocity, you have to apply a lesser force. So the formula would be static friction, and static friction is equal to Fs is equal to the mu s times the normal force, or the coefficient of static friction times the normal force, while kinetic friction is equal to the coefficient of kinetic friction times the normal force. So let's try to solve this problem. So you are trying to move a 500 Newton crate across a level floor. To start the crate moving, you have to pull with a 230 Newton force. Once the breaks loose and starts to move, you can keep it moving at a constant velocity with only 200 Newton. And note that constant velocity means the acceleration is zero, so this is still an equilibrium problem. So, what are the coefficient of static and kinetic friction? So, before we proceed, let's identify first what are the forces acting on this diagram. So, we have here the weight of the crate, the normal force of the crate, the applied force, and the friction. Since we have two cases here, so we have two free body diagrams. So the first case is we are going to try to apply an applied force when the crate is at rest. So this is the free body diagram. So the applied force here is 230 Newton, and the friction here is static friction, the weight, and the normal force. And once the crate breaks loose from at rest, so we have to apply a lesser applied force, which is 200 Newton. So the friction present here is the kinetic friction, and we have the same normal force and we have the same weight. So since there are four forces here, we cannot use the sine law method or the short method. So we have to solve using the summation of forces. So the summation of forces are forces along x and forces along y. Let's start with the forces along x. So there are two. So these are applied force, which is positive, minus the static friction, which is negative, is equal to 0. Since our problem is to find the coefficient of static friction and the coefficient of kinetic friction, so we have to get the equivalent of the static friction, which is the mu s times the normal force. So our equation will be Fa minus mu s times normal force. And since we are looking for mu s, we will derive this. So that is Fa minus mu s times normal force. And mu s, or the coefficient of static friction, is equal to applied force divided by the normal force. Let's find the given. So we know weight, which is 500 Newton. We already know the applied force, which is 230 Newton. So what is unknown is the normal force. But based on the diagram, as you can see, we can say that the normal force is just equal to the weight. And to prove that, we will go to the forces along y. So that is normal force, which is going up, which is positive, minus weight, which is going down. And we will derive this one, so we can say that normal force is just equal to weight. Since weight is 500 Newton, so therefore normal force is also 500 Newton. So let's substitute the given. So that is the applied force is 230 Newton divided by 500 Newton. Let's cancel out the units. So the answer for mu s, or the coefficient of static friction, is 0.46. So for the second case, since we have the same weight and the same normal force and the same diagram for y, I will be using my solution for the forces on y on the first case. So here we can still see that normal force is just equal to weight, which is 500 Newton. So the forces again along x on this, the applied force minus the kinetic friction. Since we're looking for coefficient of kinetic friction, so we have to find the equivalent of the kinetic friction. So that is mu k times the normal force. So our equation is applied force minus coefficient of kinetic friction times normal force. And let's derive this to find what is mu k. So that will be Fa is equal to mu k times n. And mu k is equal to applied force divided by the normal force. And the applied force in this second case is 200 Newton and the weight is 500 Newton, which is also equal to normal force. So if we will substitute the given here, so that is the applied force is 200 Newton divided by 500 Newton. Cancel again the units. So what is the coefficient of kinetic friction is 0.4. If you will compare the amount of the coefficient of static friction is greater compared to the amount of kinetic friction in this problem with the same object and the same surfaces. Okay, so let's answer another problem on friction. So crates A and B weighs 200 pounds and 100 pounds respectively. They are connected together with a cable and placed on an inclined plane. If the angle is gradually increased, determine the angle theta when the crates begin to slide. So the coefficient of static friction between the crates and the plane are, so for mu A, so this is the coefficient of static friction of crate A, that is 0.25, and the coefficient of static friction of crate B is 0.35. If you encounter problems with two masses, there should be two variables that is common to them. So later, if we will identify the forces acting on crate A and the forces acting on the crate B, the common variable on these two crates is, first is the angle that is unknown, and the second one is the tension that is connected to them. Since there are only one cord or one string that is connecting to them, so the magnitude of this tension is just the same for crate A and crate B. So that is the idea for solving this problem. So let's try to determine what are the forces acting on crate A. So that is the weight of A, the normal force of crate A, the friction of crate A, and tension. The direction of the tension should be pulling because this is the force of crate B on crate A. And let's place this in a free body diagram. So that is the crate A. Normal force is going to positive Y. Weight A is on third quadrant and the angle is from negative Y to the weight A. Static friction of crate A is to positive x-axis, and the same with the tension, which is also positive x-axis. Now, the forces on crate B are the weight of B, the normal force of crate B, the static friction of crate B, and the tension which is going down because this tension is the pull of crate A on crate B. So if we will place this in a free body diagram, so it will be, this is the crate B, so normal force is going to positive Y. The weight of B is on third quadrant and the angle of the angle theta is the angle from negative Y to weight B. Friction is going to positive x-axis and the tension is going to negative x-axis. So let's try to solve the forces acting on crate A. Now, since there are four forces acting on crate A, we cannot use the sine law method. So we will use the long method. So in this case, since we have an angle that is in between quadrants, we will get its components of this weight A. So that will be WAX, which is going to negative x, and WAY, which is going to negative y. So we will have 5 forces for crate A, 3 forces along x, and 2 forces along y. So the summation of forces along x are, so that is tension is positive, FAM is positive, and WAX is negative. So that is tension plus FA minus WAX. And we have to replace WAX and the friction since the angle is unknown, so we can get the angle from WAX and we have to get the equivalent of friction. So for that will be tension, and the equivalent of friction of A, that is mu A times the normal force of A minus the equivalent of WAX. This is WAX, and WAX will be also this one. So this is WAX. So that is opposite of the angle, so it means that is sine. So that is minus WA sine theta, which is equal to 0. If we will analyze the equation, if we can solve anything, so let's identify the given. So we have weight A, we have weight B, we have mu A, we have mu B. We don't know what is tension, we don't know what is NA, and we don't know what is angle. So it means there are 3 unknowns in this equation, so which is tension, the normal force, and the angle. So therefore we cannot solve here. So let's proceed on the forces along Y. So we have 2 forces only along Y, so that is NA minus WAY, and since there is a subscript for WA, we have to get the equivalent of this, and so WA is just the adjacent of theta, so it will be NA minus WA cosine theta. Again, we don't know what is NA and we don't know what is theta, so we cannot solve here. So let's proceed to crate B. So again, for crate B, there are 4 forces, so we cannot use the sine law method. So since there are force that is in between quadrants, we will get the equivalent of this. So that is the WB. So WBX is along negative x, and WBY, which is along negative y. So there are also 3 forces along x and 2 forces along y. So the forces along x, the positive here is friction B minus WBX minus tension. So that will be static friction of B minus WX minus tension is equal to 0. So again, we will get the equivalent of static friction and the equivalent of WBX. So that will be the coefficient of static friction of crate B times the normal force minus WB sine theta because WBX is opposite of theta. Then minus tension is equal to 0. And if we will look again the given, so there are three unknowns. So we don't know what is normal force, we don't know what is angle, and we don't know what is tension. So let's proceed on forces along Y. So we have two forces along Y, so which are the normal force, which is positive, and WBY, which is negative. So we will get the equivalent of WBY because there is subscript. So that is normal force of crate B minus WB cosine theta because WBY is the adjacent of theta. So we already determined the equation of the forces along X of crate A and crate B, and we also determine the forces along Y of crate A and crate B. So how can we solve for the angle theta in this problem? So again, as I said, for the problem of two masses that is connected with a string, there should be two common variables, so that is the tension and that is the theta. Since we are asked to find what is the angle, so we will equate them using the tension. So from here, so since the tension on crate A is just equal to the tension on crate B, so we will equate them just like this. So that the tension of crate A is just equal to the tension of crate B. So let's find out what is the formula for tension on crate A and what is the formula of tension on crate B. So since tension here on crate A is positive, so what we're going to do, these two variables, we have to transpose it to other side. So it will be tension is equal to W sine theta, which will become positive, and the mu A and A, which will, if we will transpose it to the other side, it will become negative. So this is the formula for tension of crate A. For crate B, since tension here is negative, so what we're going to do is we will just move the tension on the other side. So tension is equal to mu B times normal force of crate B minus WB sine theta. So let's substitute it to this equation. So it will be W sine theta minus mu A times NA is equal to mu B times the normal force of crate B minus WB sine theta. So in this equation, we know what is the weight of A. We don't know what is the angle. That is our problem. So we have to solve the angle. We know what is mu A. We don't know what is the normal force of A. We know what is mu B. We don't know what is the normal force of B. We know what is weight of B, and we are looking for sine theta. So we cannot solve again if we will just use this equation because there are two unknowns. So in solving a problem, there should be one unknown, and we have to replace this NA and this is NB. And to do that, we will use the equations that we have for the forces along Y. So if we will review, the forces along Y of crate A is NA minus WA cos theta, and the forces along Y on crate B is NB minus WB cosine theta. So to replace NA and NB, so we have to find the equivalent of NA, the normal force of A, and the normal force of B. So we will derive this one. So NA will be equivalent to WA cosine theta, and NB will be equivalent to WB cosine theta. So this is the equivalent of NA, and this is the equivalent of normal force of B. We will replace the value of NA with this. So we will place it here. So instead of NA, we will use WA cos theta, and instead of NB, we will use the WB cos theta. So the next equation will be just like this. So that is weight of A sine A minus mu S. So mu of A, weight of A cos theta, that is the equivalent of NA, is equal to mu of B, the equivalent of normal force of crate B is WB cosine theta minus WB sine theta. Okay, so from this equation, as you can see, we know what is weight. We also know what is the coefficient of friction. So we are only left with one unknown, which is the angle. So let's simplify this equation. So I have to place the variables here with sine, and on the other side I will place all the variables with cosine. So it means this one should be placed on the other side, which is, if I will transpose mu a, wa cos theta on the other side, it will become positive, while for WB sine theta, I will place it on another side, so it will also become positive. So it will be just like this. So that is WA sine theta, so this will 1, plus WB sine theta, so it will be the variables that I transpose on the other side, is equal to, so that is mu B WB cos theta, and since I transpose these variables on the other side, so it will become positive mu A WA cos theta. Let's factor out the sine here, and let's factor out the cosine theta. So it will be sine theta times WA plus WB, then cos theta is equal to mu B WB plus mu A WA. So what we're going to do is we will cross multiply. So we will place cos theta here below the sine theta, and WA plus WB, we will place it here. So it will be sine theta over cos theta is equal to mu B WB plus mu A WA divided WA plus WB. Now, if you will look, sine theta over cos theta is also equal to tangent theta. So the new equation now is tangent theta is equal to mu B WB plus mu A WA divided by WA plus WB. So since this is tangent, we can now find what is the angle theta. We will do the arctangent. Okay, so theta is equal to arctangent of this, and let's substitute now the given. So that is arctangent. So mu B is 0.35, WB is 150 pound, so that is already the weight. Mu A is 0.25, and mu WA is 200 pound divided by the weight of A, which is 200 pound, plus the weight of B, which is 150 pound. And the answer here is 52.5 pound plus 50 pound divided by 350 pound. So the angle is 16.32 degrees. So this is now the answer for this problem. So if you want to determine what is the tension of the string in this problem, so first you have to identify first what is the normal force of A and normal force of B. So let's try to find this one. So this is the equation for previously. So NA is equal to weight of A cos theta. So that will be 200 pound cosine 16.32, which is our answer. So the normal force of A is 191.94 pound. For the normal force on grade B, so that will be 150 pound cosine 16.32 degrees. So the normal force of B is equal to 143.96 pound. So we will use this to find the tension. So we have two equations here we have two equations of tension. So it's either you can use this or this one. So roughly they are the same. Okay, so roughly they might be. So we expect they are the same, but there in some points we are doing wrong. So we expect that the answer of these two equations for finding the tension is the same. But on the process of solving this, we rounded off some of our answers. So maybe there is a difference in decimals here for the answer of these two tensions. So let's find out. So let's solve first for the tension on using the equation for grade A. So that is WA sine theta minus mu A times the normal force of A. So that is 200 pounds sine 16.32 degrees minus 0.25 times 191.94 pound. This is the answer for our normal force of A. So that will be 56.20 pound minus 47.99 pound. So again, we rounded off again here. So the answer for the tension is 8.21 pound. If we will solve the formula for finding the tension of here, so that will be 0.35, so that is the mu B times 143.96 pounds, so that is the normal force of crate B, minus 150 pounds, that is the weight of B, and sine 16.32. So the answer here is 50.39 pound minus 42.15 pound. So the tension is 8.24 pounds. So roughly they are different with 0.3 pound because of the rounding off during the process of solving the tension. Okay, so hopefully you understand this problem.